Okay, in this video I'm going to do problem 6 here. And basically we're looking at multiplication tables modulo either 5 or 6. And when I'm in the mod 5 universe, the only numbers I really have are 0, 1, 2, 3, and 4. Anything outside of that range gets brought into that range when I take it modulo 5. And so in the modulo 5 universe, if I want to do a multiplication table, I'm going to have just 0, 1, 2, 3, and 4 in that table. Okay? 0, 1, 2, 3, 4. And so I can now fill in this table. And I'm just going to do regular multiplication, except after I'm done multiplying, I'm going to take it mod 5. And 0 times anything is always 0, so I can fill in the first row and the first column with zeros. 1 times anything is itself, so I can fill in the second row and the second column like that. Now 2 times 2 is 4, which is a legit number in our universe here. But 3 times 2 is 6, which is equal to a 1 mod 5. So I'm going to fill in the 3 times 2 and the 2 times 3. Notice that this table is perfectly symmetric about this axis, this diagonal here that goes up along the left. 2 times 4 is 8, which is 3 mod 5. 3 times 3 is 9, which is 4 mod 5. 4 times 3 is 12, which is 2 mod 5. And 4 times 4 is 16, which is 1 mod 5. And now I'm looking for multiplicative inverses here. It says we consider the table. In this way, all of our values end up in the range. We say A is a multiplicative inverse of B mod n if A times B is equal to 1 mod n. Okay? And it turns out that, notice that 1 times 1 is equal to 1. 2 times 3 is equal to 1. This is all mod 5. That 3 times 2 is equal to 1 mod 5. 4 times 4 is equal to 1 mod 5. In other words, the multiplicative inverse of 2 is 3 mod 5. The multiplicative inverse of 2 is normally 1/2. But in this world, in this strange world of mod 5, it's 3. The multiplicative inverse of 3 is 2. So 2 behaves like 1/3, and 4 is its own multiplicative inverse. 4 times 4 is equal to 1. What do I mean by a multiplicative inverse? I mean that A times A multiplicative inverse is equal to 1, which is the multiplicative identity. Normally, for real numbers, the multiplicative inverse is just 1 over the number. A would normally be 1 over A in normal arithmetic. But you can see here the funny world where these multiplicative inverses exist, and they're just some other element of the list. Okay, so some of these guys are multiplicative inverses of each other. When we go to mod 6, though, it doesn't work out as well. Mod 5, everybody has a multiplicative inverse, meaning there's a 1 in every row, except for the 0 row, of course. That's all zeros. That's never going to have a 1. But every row and every column, other than the 0 rows or the 0 columns, has a 1 in it. And that means that every number has a multiplicative inverse. And that means that the algebra that we do in a modulo 5 world is a nice algebra. And that's all I'll say about it for now, but it is nice. Mod 6 world isn't as nice as the mod 5 world. We got 1, 0, 1, 2, 3, 4, and 5. And if we make a multiplication table, 0, 1, 2, 3, 4, and 5, 2, 3, 4, and 5. It takes a few minutes to draw the thing, but I can do it. Okay, and I'll fill in the other lines, and I'm going to fill it in black again. First, our rows of all zeros. Basically, I'm just going to multiply, take my answer, mod 6. Okay, 2 times 2 is 4, 2 times 3 is 6, which is a 0, mod 6, and I'm going to fill in the diagonal. 2 times 4 is 8, which is a 2, mod 6, and 2 times 5 is 10, which is a 4, mod 6. 3 times 3 is 9, which is a 3, mod 6. 3 times 4 is 12, which is a 0. 3 times 5 is 15, which is a 3. Whoa, what happened here? There we go. I just did it like 3 times. It was saving the file. Is a 3. 5 times 3 is 15, which is 12 plus 3. 4 times 4 is 16, which is 12 plus 4. And 5 times 4 is 20, which is 18 plus 2. 5 times 5 is 25, which is 24 plus 1. Okay, now you can see that yes, 5's multiplicative inverse is 5, mod 6. But nobody else has a multiplicative inverse. 3 doesn't. 4. 2, 3, and 4 don't. Okay? 1, of course, is always its own multiplicative inverse, no matter what the base is. But 2, 3, and 4 do not. Let me try to make that a little bit better. Okay. 2, 3 to the minus 1, and 4 to the minus 1. They don't have multiplicative inverses. And the only one that does is 5. And it turns out that the GCD of 5 and 6 is 1. And so 5 and 6 are relatively prime. Only when the number is relatively prime to the modulus that you're working with, will we have a multiplicative inverse. The GCD of 4 and 6 is, I guess is 2, but it's not equal to 1. And so they're not relatively prime, and so we don't have a multiplicative inverse. There is no 1 in this 4 row or the 4 column. The 4, 1, and the 4 column look the same. However, over on the 5 side, because 5 itself is prime, every number is relatively prime to 5, and that means they all have multiplicative inverses. That's the idea here, and that's a very important launching off point into some cryptography that some of you may have coming up soon. Hope that helps.